All right. Before we start, does anybody need this questionnaire that did not get it on Wednesday? Anybody else need it? All right. Yeah, it's the About Me questionnaire. It's the same one. Yes. Perfect. All right. If you already did that questionnaire, you can turn it in to me before you leave or hang on to it until next Friday. Up to you. Let's see. I've got a couple questions about the textbook readings. Those textbook readings are not required. I have put them on there for your reference. I think they're helpful if you need a concept reinforced, stated in a different way. Sometimes the textbook will go into more context that can maybe help you understand it. But it's not required. It's only there for your use. And it's really nice. I typically don't use the textbook a whole lot. And so I like that this year the textbook is free and online, so you don't have to pay for a large textbook and then have to use it. But that is there. Right? Everything's referenced on the schedule if you want to go back and look at something. I think this textbook also has a lot of really good embedded videos and like questions to help you review. So those might end up being very helpful when it comes time to study for the exam. Any questions before we begin today? Awesome. I've already seen a few of you in my office hours, so thank you. Keep going with that questionnaire. All right, let's go ahead and begin. So we're going to start with content today. And so we're going to start very broadly. What is biology? All right, so biology, this Oxford definition, is the study of living organisms. Right? So living being the key word there, divided into many different specialized fields that cover their morphology, their physiology, anatomy, behavior, origin, distribution. Basically anything about any living organism would be considered biology. So we're going to start right away with a group activity because I want to hear from you, what does it mean to be a living organism? So what I want you to do is with those around you in groups of 2, 3, 4, whatever makes sense for who you're sitting around here, discuss this question. What does it mean to be a living organism? I'm going to give you about 2 minutes. I think I put a 3-minute timer out there, but I know why. I'm going to give you like 1 minute just to reflect for yourself. Right? Think about it quietly, jot down some ideas. Then I'll call out for you to talk with those around you, and then we'll see what everybody has come up with. Oh, I almost gave you my answers. All right, now that you have jotted down some of your ideas, talk with those around you. See if your ideas are similar or if there's some new ideas. Maybe you might want to work with the people in front of you here, the closest next to you, or you can sit down. do last night? No. I didn't think so. I don't know why I haven't started. Yeah. Communication is key, so first year. Did it happen during that time this year? It's rough. Rough way to start the season. Yeah. Nice to meet you. Yes. All right, what does it mean to be a living organism? What definitions did we come up with as groups or by yourself? Volunteers. Yeah, they can reproduce. Yeah, what else did we come up with? Functions on its own. Grow and evolve. Yeah. Anything else? Yeah, has to keep within homeostasis. Yeah, these are really great answers. I jotted down some answers up on the board here too. You actually said quite a few of them. So they have some sort of organized structure to them. Responding to the environment, responding to stimuli. They can reproduce, they grow, they maintain an internal equilibrium, so that homeostasis, and composed of cells. Right? We could go on and on. There are some that you mentioned that I don't have up there, but great. Just gonna pause so everybody can jot down notes if they want. I like this question because it can have a lot of different answers. All right, so biology. When we study biology, there are different levels of organization that we can study. We can study atoms and molecules and cells. We can study like ecosystems and communities and how species interact with one another. Right? There's so many levels of study. And like I mentioned on Wednesday, this class is going to give us a broad overview of all of these different levels. And we're going to start at the very bottom at atoms, which is why I had you watch that video before class today. In order to understand how things work, right, the physiology of a lot of these things, you have to understand atoms and how they interact with one another. So I know it's very basic. You've probably learned about the atom before, but it's a very fundamental piece of knowledge that you need to have in order to understand some of these more complex problems. So we're going to start with the atom, the smallest functional unit. right? So it's the smallest functional unit, but as you have listened to in that video, it is composed of even smaller subatomic particles, right? So up here I have the scientist who actually took the first X-ray image of an atom. You can see it's kind of like these clouds here, right? The nucleus is very, very tiny on the inside, right? The smallest functional unit. We can combine these atoms to form molecules. Right? So maybe you're like me and I've been in meetings all morning. I have not had all my coffee yet. But all these atoms, they're going to be built upon to form molecules, to form pathways, to signal, to form the whole organism. All right, so this is where I want you to watch that video so I didn't have to spell out what is an atom, what is the different subatomic particles. So I want you to take a minute, rely on that knowledge that you gain, fill in the blanks here, and then we will share our answers. And you can work with those around you, by all means. All right, so this should be an easy question. Hopefully you have learned of the atom before. Let's see, who wants to tell me what these blue dots in the center are? Yeah, protons. Oh, I guess they'll come up at once. Protons, yes, because they're positive. Protons positive, that matching letter P there. We also have those neutrons, as I've indicated. They have a neutral charge. And the electrons, and we'll spend a lot of time talking about those electrons today, and they have that partial negative charge to them. Any questions on this information? All right. So we're going to dive a little bit deeper, and we're going to continue diving deeper. So elements, right? It would be called an element if it's a pure substance, if it's made up of only one atom. Right, so of course we have our periodic table of elements here, right? A lot of these you probably will never encounter really, even in chemistry, but you'll see a lot of carbon, a lot of nitrogen, oxygen. Right, so elements made up of just one atom. Now we want to be able to read our periodic table of elements here, right? Specifically, that atomic number is going to give us some big clues. And so if I go to my next slide, right, I'm going to start with the atomic number. Right? That is going to tell us the number of protons in the nucleus. Right? It can also give us a clue, because it can also tell us the number of electrons, typically. And in many cases, not always all the case, right, but in many cases, it'll also give us a clue of a number of neutrons. Right, now there are exceptions here. So I said it's going to also tell us the number of electrons, except if our atom is an ion. We will talk about ions on Monday, but an ion is an atom with an electrical charge. Right? And in many cases, but not all cases, will tell us the number of neutrons. Right? But that atomic weight here is going to give us a bigger clue for the number of neutrons. So, atomic number, number of protons. The atomic weight, on the other hand, is the average weight of all the particles in the atom. And it's really helpful in specifically finding the number of neutrons. A lot of times, the number of protons and neutrons will be equal, but a lot of times they will not be equal. There's one easy way to do this to find the number of neutrons. You would round the atomic weight, right? So round it to the nearest whole number. So in this case, we would round it to 16. Right? So 15.999, round it up to 16. And then we subtract the number of protons. So if we did 16 minus 8 protons, it would leave us with our 8 neutrons. Right? That's a nice, easy way to figure out the neutrons. And like I said, a lot of times, they will be the same number. Right? More often than not, you might see it's off by like a number or two from the number of protons. And then, of course, we have the easy bits. All right? We have our symbol, the 1 or 2 letter symbol of the element, and then we have our name. Now, you might see different versions of this. So, for example, the atomic weight might be on the bottom. Right? So, always important to note that the whole number will be the atomic number. Any decimal number will be the atomic weight. All right. So this is important when we think of an atom, what fundamentally makes up a different element from each other. So if we have, we're going to take the sodium atom here. Right? It has 11 protons, 12 neutrons. If we take away a proton, right, it's going to become a completely different element. It's going to become neon. Right? Same if we were to add a proton. It's going to become a completely different element. Right? It would be a magnesium element in this case. Right? So protons, if we manipulate those in any way, we're going to change into a different element. Versus the electrons, right? We can take away some electrons. We could add some electrons in. It's going to stay the same element, but now it's going to be an ion. So an element with a charge. And again, we'll elaborate that with that on Monday when we start talking about ionic bonds. Right? But essentially, they're either missing a couple electrons or they have gained a couple of electrons, giving them a charge. Right? So take away an electron, stays the same element. Take away a proton, it's going to be something else. I know we're still doing some of this basic terminology here. Hopefully we all know what the nucleus is, right? It's the center of the atom. It contains those protons and neutrons. I liked that video that I had you watch where it kind of gave you a sense of the scale of the nucleus. I think it was like a house spider in the span of 8 football fields, right? Would be how small the nucleus is compared to the whole atom. So it's pretty tiny. Right? And like we said, usually, not always, the number of protons will equal the number of neutrons. So nucleus, pretty basic. I'm going to keep moving us along here. You can kind of think of an analogy here, whereas the nucleus, if this were an atom as a hotel, the nucleus would be the welcome desk, right? Where everything is kind of centralized. All right, the next aspect of the electron here would be the electron shell, or excuse me, the atom would be the electron shell. These are going to be regions surrounding the nucleus, right, that hold the electrons. And they're going to hold a set number of electrons, depending on how far away that shell is from the nucleus. So you can see here we have 2 electron shells in our atomic structure of nitrogen. And you see this first electron shell has 2 electrons. This second electron shell is holding more electrons. Right, so it's these regions surrounding the nucleus. If we think about our analogy, it's kind of like the floors of a hotel. Right? We're getting further away from that welcome desk. I wanted to point out these electron shells can sometimes, you might see letters naming each shell, right? We're not going to go into the letters naming them, but as you're studying, you might come across this shell is the K shell and the L shell, right? Know that that's just a way to name these shells. These shells also have different amounts of energy associated with them. With the ones furthest away from the nucleus, having a relatively higher amount of energy than the ones closer to the nucleus. Right? And we will see this when we start talking about photosynthesis, right? How this matters and how this can be used by organisms. Right? But I just want to make you aware that sometimes you might see n equals 1, meaning it's the lowest level of energy. But the biggest thing I want you to take away here is that these outer shells, the further you go away from the nucleus, can hold more electrons. So the inner shell can hold 2. Right? Outer shell can hold up to 8, no more than 8. Once we get more than 8, we gotta go to yet another electron shell, 18, and then 32, and then 50. Right? So they can hold more electrons. All right, within these electron shells, we are going to find orbitals. So orbitals are regions of high probability of finding electrons. Right? So they're the regions within the shells that you can find clusters of electrons. Right? These orbitals, they hold electrons, but they can only hold a maximum of 2 at a time. Right? So they can have just 1 electron, but they can only hold a max of 2. So if we think about that analogy again, right, it's like on each floor of a hotel, you have a room, and the max occupant is 2. Right? Only 1 person could stay in this room, but at max 2. Now, orbitals come in different shapes. They're not as simplified as I have been showing you. They actually come in all these different forms surrounding the nucleus. Right? This is not a chemistry class. We're not going to dive into this, right? But these orbitals are generally these localized areas, right? They might have kind of a ring structure to them. They might have these balloon structures going out. Right? There's different regions. Just like in our analogy, we can have different types of rooms, right? You can have a suite, you can have 1 king bed, you can have 2 queen beds, so on and so forth, right? So I want you to be aware that what we are looking at is a very simplified way of looking at orbitals, right? So we have our atom here, we have our nucleus in the middle, we have 3 electron shells, right? And we can see in this Bohr model, right, that means this way, this format of drawing out an atom, they tend to be clustered into groups of 2, indicating the orbitals. Right? It's much easier to look at an atom in this model versus trying to interpret something like these cloud diagrams. Right? And I'm coming back to this one because I want us to see, as we go further out in these shells, they can hold more electrons and thus can hold more orbitals. So if I want to figure out how many orbitals were in the 3rd electron shell here, I can see that the number of electrons that it can hold is 18. I know that each orbital can only have a maximum of 2 electrons. So we go 18 divided by 2. I know there would be 9 orbitals there. All right, this will be important when we try to draw out our atom. All right, some more on electrons here. If we look at nitrogen here, we have this outer shell, right, and we have these electrons in this outer shell. These are the valence electrons. So these are really important for forming bonds. And we will get to how they form bonds later on today. Right, but they're the ones on the outermost shell. So if you hear the words valence electrons, only talk about the electrons furthest away from the nucleus there. All right, any questions about the terminology? I'm going to give you a chance to put this into practice in a little bit here. All right, I think one way to put this into practice is drawing an atom based on what we see on our periodic table of elements here. So we're going to go through a couple examples, and then I will have you do a few more on your own. We're going to draw helium first. All right, so what I like to do is I like to look at my atomic number. I see it has 2, right? So I'm going to put my 2 protons there. If I look at my atomic weight, which is 4, minus my atomic number of 2, I know that I will also need 2 neutrons. So I can add in my 2 neutrons. I then have to think about my electrons. Right, so I can start by putting my 1 electron shell out there. And again, if we see the atomic number of 2, it also tells us there's 2 electrons. So I can put 2 electrons in my outer shell there. Right, I know that this first shell can only hold a maximum of 2. So I'll put my 2 electrons there. Right. Now I like to simplify it. You can draw it like this. You will see drawings like this. But I like to simplify it by grouping them together so I know that they are both in the same orbital. All right, so now we have our helium drawn. Helium, one of the easiest ones. Let's do one that's a little bit more complex. We're going to do oxygen. All right, so again, I'm looking at that atomic number of 8. I know I have 8 protons. Right? I take my atomic weight, I round it up to 16. Right? I subtract the 8. I know I also have 8 neutrons. Right? So I'll add those in. I'll add in my first ring, my first electron shell. And again, I know I can hold 2 electrons here. So I'm going to put those 2 electrons in that first electron shell. Right? And again, I like to group them in pairs of 2 so I know how many orbitals, just makes it easier to see. But I know I have 8 electrons, and this only accounts for 2, which means I have to move up to the next ring. Oh, nice little animation there. I have to put another electron shell there to hold the rest of my electrons. Right, so now I'm up to my second electron shell. It can hold up to 8 electrons. Right? We don't have 8 remaining, but it will hold the remaining of our 6. So I can put that in there. I like to start by putting 1 in each orbital first. So if I have 8 electrons that this shell can hold, and each orbital can hold up to 2 electrons, 8 divided by 2, we get 4. We know we will have 4 orbitals. So start by putting 1 electron in each orbital first. There's second electron, third in this shell, fourth in this shell. Now we can go in and add a second electron to accompany these orbitals and fill them up to max capacity. Right? So I'll add in my other electrons there. All right? Yes? You could, yeah. So instead of I just chose the top and the side here, you could start by filling in the bottom one on the other side. Right? All right, so now we have our oxygen atom draw. All right, I want to give you a chance to put this into practice. So what I want you to do, again, with those around you, talk this through. It's always helpful to talk information out loud. I want you to go through these 4 atoms here. I want you to draw them. I want you to tell me how many protons, electrons, and neutrons does it have? How many electron shells? How many orbitals does it have? And is the outer electron shell full? So is that shell at capacity for its electrons? All right, if you get done early, I put a bonus one over here that you can work on as well. You'll notice that that next slide, if you're making notes directly on slides, does have a chart where you can fill in some of your answers. All right. Now, I'm going to give you like 10 minutes to do this because I want you to make sure you understand this knowledge before we move on. If we get done before 10 minutes, great, but you have plenty of time. And work with one another. It's quiet in here. I'm going to dim the lights a little bit because it is a little bright. Ooh, that can be quite a bit, but as long as you don't fall asleep on me. Yeah, the outer shell is always the last one. So depending on the atom, I have up to, it's 30. Always start by getting it one, and then adding a partner. So it could be an orbital that only has one. Have at least one first, and then the second. I use this time. Yes. Did anybody get the phosphorus? Yeah? Good. I wasn't sure how far you did in this 10 minutes. I gave you a large chunk of time. All right, let's go over some answers. Oh, that one's going to pop up first, apparently. We're going to start with neon here. How many protons, electrons, and neutrons does neon have? 10. Does it have 10 of each? Oh, my animations are all wrong. Okay. Well, we'll come back to neon, but we'll say 10 of each. All right, we'll double check that. Let's start with fluorine, because that looks like it's the next one to pop up. Let's see. How many protons, electrons, and neutrons does this one have? 9, 9, 10. Yeah. You might have saw that already, too. All right, so 9, 9, 10. How many electron shells does it have? Well, we know it has 2. Right, so to fill up that first shell, we'll have to bump it into the next shell to put the rest of the electrons. All right, we're just going to go over the answers, I think, because the animations are so wrong. But if we look at the drawing here, right, we can see that we have 1 orbital in that first shell, right, and then we have 4 more orbitals in that last shell. Right? And why am I saying that the outer shell is not full? Because one of them is only half full. Yeah, one of those orbitals there, right, is not filled. So it's not a full electron shell. So sodium here, if we look at those, that's sodium. Gosh. All right. So we can see that sodium, 11 protons, 11 electrons, 12 neutrons, right, because we subtract 11 from our atomic weight, rounded up to 23, we get 12. This one, we have not only filled up that first electron shell, we've also filled up the second electron shell, and I've had to move into that third electron shell. Right, so total orbitals, again, I'm counting up those pairs of 2. Right? I see I have 6, even though 1 is not full. Did I miscount? Okay, I thought I saw some confused faces. Right, and I know that this last electron shell here, it's not full, because we have an orbital that's missing a pair, and we know that this third electron shell can hold many more electrons than just the one that's currently there. All right, boron here. Right. Again, if we look at the drawing, we see we have 2 electron shells. We had to bump it up into 2. Our first one is completely full. Our next one isn't full at all. Right. And hopefully when you've drawn this, you first added in an electron to 3 of these orbitals, but then you ran out of electrons. So you're going to have an empty orbital, right? And the 3 orbitals that you do have, right, are not going to be full. You're only going to have 1 electron. Right? So if we were to count up the ones with electrons, we see we have 4 orbitals in our 2 electron shells. Now for those of you that got to phosphorus, it's a bigger one, right? Lot to draw. And we can see we are still in the 3rd electron shells here. Right? And that electron shell, once again, is not full. Same as what we've been talking about for those others here. We have 1 that's full, right? And then we have a couple others. All right, any questions here? Oh, let me show you the answer for that one in case you want to jot it down. All right. So we could do this for every atomic element. I'm not going to make you do the elements that have more than 20 protons. That's a lot of drawing. Okay. But you should know how to draw some of these easier ones with at least 11 protons, right? We can draw 11 dots and then 11 more for the neutrons. No, so every shell after the next one will hold more than that. Are you looking at phosphorus here by chance? I'm noticing this too when I just was talking. So if we look at phosphorus, right, this outer shell, we added in another electron for a pair here, and that should not be the case. I don't know why this drawing decided to do that. I don't know if it was to make it look even and aesthetically pleasing, right? But you should have 5 orbitals that only have 1 here. So it's a little off there. So you got that bonus one, put a little asterisk next to it, make sure that you remember that we actually should have 1 orbital here, 4 in the next one for 5, 6, 7, 8, 9, and then 10, because that shell can hold more electrons. In fact, let's go back. Ooh. That's a great question, and I did not pick up on that when I was making this slide. All right, we can see this third one here. It can hold 18. So it could have a maximum of 9 orbitals. So I'm not sure why that drawing decided to pair up one of them. That's a good observation, though. Any other questions? Hopefully that didn't confuse you more. I'd say practice, practice, practice. All right. So, elements in our body, if we think of the really common ones, right, I thought this graph was really interesting in that if we look at the human body mass, right, most of our body mass, right, approximately 95% of our total mass is only made up of 4 elements: oxygen, carbon, hydrogen, and nitrogen. Right, so that's kind of a crazy statistic. And then all those other elements, we call them trace elements because they make up for less than 0.1% of the total mass, or that other 5%. Right? So we have ones that will show up way more commonly than others. All right, I wanted to put a link in here to this game. We're not going to go through it, but I will click on the link. I found that this game was actually super helpful. And so if we were to click on this link, I would encourage you to look at this when you are studying atoms. It's this nice simulation game that maybe it won't load for us. There it goes. Where you can quite literally build an atom just like you were doing, right? So you can add in a proton, right? Add in an electron, add in a neutron, right? And you can see that the element will change if you add in another proton, right? So we'll give it another neutron. But that element won't change if we, right, play around with electrons. Simple animation. I'd encourage you to play around with it. So I linked it directly in the slides there. All right, let's move on from atoms. Let's start talking about molecules. All right, we're going up one step at a time. Any questions before we go on? I think I already asked this. All right, let's talk molecules. So, a molecule, right, let me turn on my captions, are when we have 2 or more atoms bonded together, right? If we say it's a compound, right, it's going to be a molecule with more than 1 element, right? So I could say that this sodium hydroxide here, right, it has oxygen and hydrogen. This is a compound. I could also say it's a molecule because it's more than 1 atom bonded together, right? Properties of an element combined with other atoms can drastically change how it's going to react as compared to a pure element, right? So sodium, if we add it with oxygen and hydrogen here, it creates sodium hydroxide, which is something you would not want to ingest. But if we combine the sodium with chloride, we get table salt, which is relatively harmless and something we actually need in our bodies. right? So we're going to talk about how we combine them together. So we're going to start by talking about chemical bonds, and we should get through at least one type of bond before the end of lecture today. So if we think about bonds, we have to think about this electrostatic force, right? The attraction or repulsion between two objects that have a charge, right? So if we look at this nice diagram up here, we see that like charges, right, they repulse each other. So think about the protons in the nucleus of the atom. They are exerting a repulsive force. Same with the electrons. The electrons, they're exerting a repulsive force because they are the same charge. If we look at this electron compared to the proton in the other atom here, there's a slight attractive force because opposites attract, right? Now molecules, they like to be in a stable state, right? So they like to have what we would call a potential energy that's very low, right? Minimizing the amount of chaos, the amount of attraction and repulsive forces in them. So I like this diagram because we see the amount of energy on our y-axis here and the distance of our molecules apart from each other on our x-axis. And we can see when our molecule or when our atoms are really close to each other, they exert this really high repulsion force, right? Our protons are repulsing each other, our electrons are repulsing each other, right? That's relatively unstable. It has a high amount of energy associated with it. Now molecules, they like to be stable, so that's not the best configuration for them. But if there's no overlap of our atoms, right, so they're not coming in contact with each other, right, they might have a relatively stable potential energy, right, but there's no attraction, right, you can't make a molecule that way. So we do have to have some attraction and some overlap, and it's a balance act between those repulsive forces and those forces that attract one another. Right? Now we're going to talk about those three bonds, which, again, if you've taken a class before, this is likely not new information, but it's information that we are going to continually build upon this semester. So the first one we're going to talk about is our covalent bond. Right? Our covalent bond is bonds between atoms where they are sharing their electrons. Right? And this is why I asked you, is that outer electron shell full? Right? If it is not full, they have the ability to create these covalent bonds because they can share atoms or share electrons. Right? You see this fluorine atom here, this hydrogen atom here. The outer electron shell, they are not full. Right? You see at least one orbital that does not have a pair to it. Right? So they can share those electrons, right, and thus bond together. Right? This makes a very, very strong bond. In fact, this is one of the strongest bonds that we can have. Right? And if we look at a variety of atoms here, hydrogen, oxygen, nitrogen, carbon, right? They're all trying to essentially fill that outer electron shell. Right? So they want to bond with other molecules. So for hydrogen, that means it can make one bond with another atom to fill its one missing electron from that orbital. Right? Now as we go up, say, to carbon here, we see that this outer shell has 4 orbitals, right? But the orbitals only have 1 electron each, so it's not full. This carbon atom could make 4 bonds in order to completely fill that electron shell. And again, they're sharing these electrons, right? So if we're sharing, we're making a strong bond, right? And again, we can have single bonds, so we can share 1 electron, such as in this water molecule, ammonia here, right? Methane. You see this carbon we just talked about, it's making 4 bonds, right, in order to keep that electron shell full. We can have double bonds, right? So they're sharing 2 pairs of electrons with the same atom. We can have triple bonds, right? We're sharing 3 pairs of electrons with the same atom. Right? So there's variety within our covalent bonds. This next concept here is one that we are going to go back to time and time again. Electronegativity. So they're sharing their electrons, but what is the attraction to share those electrons? Right? We would call this the electronegativity. The attraction for shared electrons. So essentially, how badly does that atom want an electron? If we look at a periodic table of elements, there's a trend here, and I don't expect you to memorize this trend. But as we go down in our columns, we're decreasing electronegativity. And as we go to the right, we increase electronegativity. Okay? So atoms have differing electronegativities, or a differing of the need to share electrons. Right, so for covalent bonds, right, if we have an atom here, right, we have carbon bonded to these other atoms of hydrogen, right, if we look at their relative electronegativities here, right, carbon has 2.55 of electronegativity, hydrogen has 2.20, they're really close together. Those are really similar electronegativities, right? They have a similar attraction to share electrons, which means they're going to share those electrons equally, right? It's an equal exchange. So in this type of bond, we would say this is a non-polar covalent bond, right? We are sharing electrons equally. But some atoms here, as we see on our list here, and I'm always going to give you this list of electronegativities. I don't expect you to memorize these, right? But if we look at our list, oxygen has a really high electronegativity of 3.44, right? Compared to what it's bonded to in the water molecule of hydrogen of 2.20, right? This has a higher electronegativity, which means it wants those electrons more. It's essentially going to hog those shared electrons, right? So those electrons, they're not going to be shared equally. It's going to be an unequal sharing, which means we're going to get a molecule that is polar, and we would say this is a polar covalent bond. Right? So again, polar covalent bonds happen when atoms have strong differing electronegativities. So the electrons are essentially going to be closer to that atom, so this being oxygen here, and bound with 2 hydrogens. Oxygen has that higher electronegativity. It wants those electrons more, so those electrons are going to be closer to the oxygen atom than it is to the hydrogen atom. Right? Now those electrons are negatively charged, and if oxygen is hogging more of those negatively charged electrons, this side of our molecule, the side where our oxygen is going to be more negative than the hydrogen atoms, right? Because the hydrogen atoms are taking those negative charges and it's further away from them, right? But the oxygen's hogging it, so it's closer to the oxygen. The oxygen is going to be partially negatively charged. Hydrogen is losing some of that negative charge, so it's going to be partially positive. All right. So if we take a look at these molecules here, you will see that they have this delta symbol here, delta negative, indicating that it has a partial charge that is negative because it has more electrons closer to its nucleus. Right? It's pulled it away from the hydrogen, so those hydrogens have fewer electrons closer to it, which means it's going to be partially positive. So think of it kind of as a tug of war, right? They're both trying to have these electrons, but oxygen is stronger, so it's going to have those electrons closer to it. All right, I did another simulation in here, and this one I actually kind of want to go over with you because I think it's a great simulation. It loads quickly. So I think if you're having trouble understanding this concept of electronegativity, because we are going to base a lot of different bonds and molecules and how they interact and work with each other on this concept, play around with this simulation. So I'm going to do 3 atoms here. Right? And I can say the electronegativity for all of these. So atom A is going to be relatively less electronegative. Same with atom C versus atom B is very electronegative. So I'm going to click partial charges. I can see that means because it's hogging those electrons, it has that negative charge. Now if I made them all the same, there would be no partial charges because they're shared equally. This would not be a polar molecule. Right? I could make atom C, right, very electronegative. Right? And because it has more electronegativity, it's going to hog the electrons and be negative. Right? So I really like this simulation if you're having a hard time understanding this interaction. Right. Beyond that, I'm going to give us an opportunity to practice. So for each of these molecules, I want you to determine, is it a polar or nonpolar molecule? And if it's polar, tell me which atom these shared electrons are going to be closer to. Right? And so you can put a little negative sign by that atom because it's hogging those negatively charged electrons. So take a few minutes, and then that will probably bring us to the end here. I might cut us off at like the 3-minute mark from this timer. Yes, it is. That doesn't show up very well, does it? No, not even you. When it's projected, it's really hard to see. I can't remember it off the top of my head. Yeah. I'll have to answer that next class period, because that's a great question. Yeah. review these at the start of next class period. Great question. No homework for Monday. Enjoy your weekend.